0, where a random backup value in between 0 to W0 minus 1 is randomly chosen. When a success occurs after the transmission occurs when the backup counter value becomes 0, the station actually transmits. So the state of the Markov chain is represented by its stage S of t and its backup counter value B of t. So this pair of values actually represents the discrete time Markov chain. After every slot time, the state of the Markov chain is decreased by 1 if the current slot is a free slot. If the current slot is a busy slot, then a transmission starts. Then after SIFS, an ACK is transmitted, the data. Then after DIFS, the station actually decrease the value of the backup counter by 1. So here actually the slot time is this one. This is also a slot time. And the backup value is decreased by 1. So by this way, the backup value is decreased. One important thing is that the chain can move from 02 to 01 only. From 01, it can go to 00 only. So the probability with which the backup values are decreased is always 1. That's why if the chain starts somewhere here, then eventually with probability 1, it will come here. The probability is 1. And once it will be here at the state 00, this one stage is 0, backup counter value is 0, the station transmits. Once the station transmits, there are two options. With a probability P, a collision occurs and a stage is increased by 1. When a collision occurs, the stage is increased by 1. So we move from 0 to 1 or I to I plus 1. At the same time, what we do, we settle a backup counter value randomly. We settle a backup counter value randomly, and when the backup counter value reaches 0 again, the station transmits with the probability P, a collision occurs, and a random backup counter value is chosen, or with the probability 1 minus P, a success occurs, and the node goes to, the station goes to stage 0 and start the transmission of the next packets. So by this way, it keeps going. Now question is, if we want to solve this system of linear equation associated with the Markov chain, actually we need to consider thousands of states, and the transition probabilities for thousands of states needs to be mentioned. So here the interesting thing is that all the states up to this, starting from here to here, always the backup counter value is decreased by 1, 2 to 1, 1 to 0, just after one slot, as we define this. Either a slot can be this one or a slot can be this one. A transmission by other station or a collision by other station, or a frame is actually a free slot is there. So with probability 1, and very intelligently it is mentioned here in a single line, 90% of the states probability transitions are given. What is this? If your current stage is I indicates your stage. It is 0, that means that you are dealing with a fresh packet. It is non-zero, that means packet experiences some transmissions. So when stage is equal to 1, that means you are now attempting to transmit a packet which has experienced one collision. So the stage is I, and if your current state is k plus 1, sorry, if its current backup counter value is k plus 1, then after one slot time it will be k. So the backup counter value will be decreased by. On the other hand, if your current backup counter value is 0 and you are in a stage I could be 0 to m any value, then actually this indicates a transmission is imminent. That means the station will transmit. So when a station transmits, we know there are two cases. After transmission, a success, a failure, or collision. A collision occurs with probability P, a success occurs, a probability 1 minus P. So if a success occurs, then the stage I will be, okay, let me write it here, I will be 0. That means the packet is gone, transmitted, and now you need to choose a new packet and then start the transmission of that packet. Okay. Now, so you change the stage from I to 0. And when you choose I to 0, then you do another thing. You choose one of the backup values in between 0 to W naught minus 1. So there are W naught possible values. If you choose uniformly, one of the value will be chosen with probability 1 over W naught. With the probability 1 over W naught. And a success occurs with the probability P. So with 1 minus P. So with the probability 1 minus P divided by W naught, you choose a number K. And this K is in between 0 to W naught minus 1. So you choose a value of K in between 0 to W naught minus 1 when a success occurs. On the other hand, when a failure occurs, your current value of BP equal to 0, and now you are in a stage I minus 1. So since a collision will occur, success will occur, then we are in here. So this line is for a success. This line is for a collision. When a collision will occur, then actually you need to increase your backup stage from I minus 1 to I. From I minus 1 to I. That means you increase the stage by 1. And once again, you choose a backup counter value K. However, now the K is in between 0 to Wi minus 1. So unlike this one, when after successful transmission, you choose in between 0 to W naught minus 1. Now you choose a value of K in between 0 to 2 to the power I W naught minus 1. And finally, there is a row here, which actually is when you reach the maximum backup counter value, which is for 822.11 is 1024. What you do, you do not increase the backup window size, rather you keep there, and the diagram here shows that when you reach M, you actually, with probability P, you choose a backup window size in 0 to W M minus 1. So when you come here from M minus 1 to M, from M to M, the similar actually window size remains. So one assumption here is a frame is never discarded. However, in 822.11, after a number of R minus 1 retries, a packet is discarded. But here, the model is assumed that the packet is never discarded. This is okay. So this sort of assumption actually is not violating the DCF, but this is true. So once you have this one, then these four equations very intelligently represents the probability transition matrix for these thousands states. In which state you will go with what probability to what state. And these just four equations very intelligently represent the probability transition matrix. And here we have the probability state transition graph. Now, once you have this one, then actually, how do we analyze the performance? We want to actually analyze the probability tau, probability that a station transmits. What is the probability that a station transmits? And we want to do it for long time or a steady state probability. Then you need to calculate the steady state probability of all states. Actually, we are not interested about these steady state because a station transmits when the backup state value is 0. So just we want to know the probability that the chain is here. And this says the probability with which a station transmits. We will not go into the very detail of the analysis. Uh, this tau is the probability that you are in this stage and following the paper. You do not need to actually memorize this or like this one. If you are given a problem, then it will be very simple. You do not need to analyze this paper for this calculation because the equations are very sophisticated. So somehow they find out that the probability that a station transmits. Once you have the probability that a station transmits, then many things can be calculated. What is the probability? What are these? The first quantity that we can actually calculate is PTR. What is PTR? Probability that there is at least one transmission in a particular slot time. So if this is a slot, random slot, what is the probability that there is a transmission there? So a transmission will be there if at least one station transmits. So what is the probability a single station transmit? Is tau. What is the probability that a station does not transmit? 1 minus tau. What is the probability that n station does not transmit? Do not transmit is 1 minus tau to n. And then 1 minus tau to n is the probability that at least one station transmit in a random slot. Now, PS represents the probability that there is a successful transmission. The probability that a transmission occurring on a channel is successful, probability that exactly one station transmit on the channel. So when there is a single station transmitting in the channel, previously what we did, we calculated this one PS as N A 1 minus A N minus 1. Right? This is the probability that a single station transmit. But here, the probability of success is calculated actually using a conditional probability. How? This conditional probability PS is the probability that if there is a transition in a transmission in a slot, what is the probability that a single station transmit? So probability that a single station transmit, given that at least one station transmits. That means this PS actually is equal to probability that a single station is transmit T1, given that two or one or more stations are transmitting. So this is now this paper define the probability as a conditional probability. So what is the probability? This one actually is calculated by this way. In the numerator, we have probability that a single station transmits, that is like this one. And tau is the probability that a station transmit, 1 minus tau is the probability that a station not, and n minus 1 is n minus 1 station do not transmit. And TR is the probability that at least one station is transmitting. So by this way, we can calculate the probability of success. Now, how can you express S? What is S? I think S is the successful bit transmitted in a slot. And then in a slot, what is the length of a slot? This is one thing. The length of a slot actually is variable. Here, a slot can be of length sigma. That means a free slot during which a station actually check whether the channel is free or not, and it actually decrease the backup counter. Then we have a slot time.
Hello.
This is
It's good.
defined as the payload time, successful transmission time. Another one is collision time. What are the definition? Let me. EP is the successful transmission time, and this indicates the DIFS, free time, transmission time, SIFS, and the ACT transmission time, with the assumption that RTS, CTS handshaking are not used. If you use the RTS, CTS handshaking, then the probabilities, then the duration will be changed. And TC is the collision time. So what is the expected actually time of a slot? This is the free slot. A free slot occurs with a probability 1 minus PTR. That means no station transmits. A successful transmission occurs with a probability PTR. That means there is a transition and there is a success. Now, if we put this together, PTR times PS, then actually come here. When we multiply PTR and PTPS, then actually this one is multiplied by PTR, this quantity. So this quantity and this quantity cancel out each other. So probability of success, actually, even though that means a successful transmission occurs with a probability, not this one, let's say P prime is once again like other, the previously we assume is same as this one. So PS times TR is the probability that when there is a transmission, a success occurs. That means probability of a successful transmission is this one. And then we have the probability of a collision. If there is a transmission which occurs with the probability PTR and success does not occur, that means 1 minus PS, so a collision occurs. So among this expected time, only this time period actually valid data is transmitted. So we call the throughput. Fraction of time successful data are transmitted is this one, is the uh, is the throughput of the system. Now, at this point, I like to hear questions from you if there is any. The paper has many internal calculations, especially for this tau and this one. A few equations are here. Do not concentrate there because these equations are very sophisticated and it will require days, if not weeks, to understand this. Assume that we have a probability tau. We have a probability tau that a station transmits, that in general is I is equal to 0 to m. That means VIN. So whenever the station reaches the backup counter value 0, it transmits. So probability that a station transmits is when it reaches this backup counter value 0. So if you have any questions, please. Any questions? So if you do not have any questions, then with this, actually, we finish the performance analysis of MAC layer protocols. And we covered Aloha, slotted Aloha, CSMA, CSMA-CD, CSMA-CA, CSMA-CA with two versions, totally different. First one is actually a simple one, does not consider the backup process in detail. But in the second one, we have a very sophisticated escape mechanism. Now consider if you are asked to find out the probability that a station transmits tau and the throughput if we consider that there is no retransmission. That means only the first line exists. Successive lines do not exist. I think then you can easily calculate it. So since you do not have any questions, let us move on to the second part of this chapter where we actually calculate we analyze different error control protocols. The protocols are very basic, very simple. Though these protocols are widely used. For example, this go back and ARQ is a modified version of this one, actually is used by TCP. So we have three protocols, end-to-end protocols. These end-to-end protocols, what they do, they actually ensures two things: guaranteed and in-order delivery. When a station or a node on application, more specifically, has a sequence of packets, these automatic repeat request protocols or techniques or mechanisms actually ensures two things: that the packets are delivered with guarantee and they are delivered in order. So even though the sequence of packets are actually somehow altered during the transmission from the host to the destination, because uh, uh, a packet or packets from a single source, a single application might travel different paths. So the order in which they actually arrive the destination might not be the same as the order in which they are sent at the source. Now, the stop and wait protocol is a very simple protocol. Just we have a station here, A and B. A sends a packet. After sending the it stop and wait. Wait for what? So data is sent. Wait for the acknowledgement. Only when the acknowledgement is received, it sends the next packet. So D1 is here, D2 is here. Unless otherwise an acknowledgement is not received by sender A, it is not allowed, it is restricted to proceed further. So it has to retransmit data packet 1 and it has to repeat that one again and again until it is received. So both guaranteed and in order delivery is there. And it is assumed that if the transmission time is much larger than the propagation time, then actually this condition is this one. The transmission time of a packet, tau t, is the round trip time. This is the TP is the tau p is the propagation time. 2 times tau p is the round trip time. So if the round trip time is much less than actually the transmission time, then actually what happens? A packet that starts here, actually the whole channel actually is occupied. Before the station stop transmitting the packet, the front side of the first bit of the packet is reached by the destination. So most of the time channel is kept occupied. And so it can work, but the efficiency of the protocol is very less. So our objective actually is to analyze this one using a Markov chain once again. So this is called stop and wait. You send a packet and stop. Then you wait till the acknowledgement of the packet is received by you. Once you receive the acknowledgement, then you send the second packet and again stop after sending the second packet and you wait for the acknowledgement. If the acknowledgement actually is received, then you go for the next. If the acknowledgement does not receive, what you do is transmit. Now, some system uses acknowledgement and negative acknowledgement both. Some system uses acknowledgement and timeout. The timeout is also required here because in both ACK and NACK can be corrupted. Then the sender will be waiting for the ACK or NACK. The receiver has already sent it, so there will be actually infinite loop. So what happens? A timeout is there. If timeouts, then the sender is transmit the previous packet. Go back and actually the sliding window protocol. What it does to increase the efficiency, it has a window of n packets. and it can transmit n packets one after another or simultaneously. One after another is a better term. And all the packets will be in transit. It can transmit n packets before receiving any acknowledgement. If you receive one acknowledgement, then it can again send another packet. So by this way, a window actually either shrinks or a window actually slides. And a station is allowed to send more than one packets one after another. This actually increases the efficiency. Now the protocol is named as go back in when there is a negative acknowledgement. The negative acknowledgement actually always will indicate. So if the acknowledgement sends the packet number n, then the sender has to retransmit packet with ID n and all the subsequent packets. Now consider a packet say 1, 2, 3 has been sent by the source one after another. And if a negative acknowledgement actually comes with the ID 2, this indicates that this sender has to retransmit packet 2 and all the subsequent packets, that means 2 and 3 has to be. The sender will then send again 2 and 3. Now one important thing is that if the number actually go back n, this go back n actually represent 2, that means it acknowledges all the packets up to 1 has been received. Now it is waiting for packet 2. And the sender not only will retransmit packet 2, it will also retransmit all the subsequent packets. So the problem is, if there are, say, window size is 10, only the first packet actually is corrupted or lost. All the subsequent packets have been received by the source. Then, receiver. Then the source not only will retransmit packet 1, but also all the successfully received packet. So a very easy solution is that a selective repeat error correction mechanism can be used, where the sender can explicitly tell which packet to retransmit. The mechanism will be very difficult to implement, but the efficiency will be increased. As I mentioned in the last class or last to last class, that in earlier days, the major intention in designing a networking protocol was to keep the protocol as simple as it is possible. Nowadays, machines are powerful. Things can be done very easily, but at the time, most of the devices actually had very limited capability. Anyway, so we will analyze these three, sorry, we will analyze these three error correction mechanisms, we usually call ARQ, automatic repeat request. TCP uses a sliding window protocol, but the protocol itself is not like this one. It uses, can anyone tell how TCP actually implement these two things, guaranteed and in order delivery? Everybody is sleeping? Or wait for the Johor prayer? Okay, TCP actually has a very sophisticated mechanism. We call it slow start. Then it increases with a very low packet rate and then gradually increase the rate at a very aggressive way. We call it slow start. And then actually when a packet lost, there are mechanisms we call triple duplicate acknowledgement. Timeout mechanism also is there. Fast retransmission mechanism also there. And TCP actually has many versions, TCP Reno, TCP Tahoe, TCP Neurono, and many others actually nowadays very sophisticated extensions of TCPs are available. But eventually, TCP uses actually one of the sliding window protocols. So let's begin with this stop and wait. I hope at least few are listening. In stop and wait protocol, as I mentioned, this condition has to be satisfied. The round trip time should be mass less than transmission time. Otherwise, most of the channels will be kept idle channel time. By this way, at least a majority portion of the channel time will be kept busy. If the transmission rate is very less, propagation actually occurs at a speed of light. If d is the distance, then the propagation delay will be calculated by this one. C is the speed of light, d is the distance. On the other hand, transmission actually delay depends on the length of the packet and the transmission rate. So if there are 500 bits, lambda tells you number of bits sent per second per unit time, then you can know the transmission delay. Once you have this one, then the operation of stop and wait ARQ can be explained in this way. Here we have the transmitter, we have the receiver. In the middle, let us assume that the channel is there. So the sender send a packet and wait for the receiver. After receiving the packet, check the packet actually by comparing CRC or checksum, depending on whether you are using this one in layer 2 or layer 4 of the TCP/IP protocol suite. Then, if the packet is successfully received and acknowledgement is sent, okay, the sender then transmit packet to. The packet to somehow was corrupted, following this example, and this receiver sent a NAC. The NAC itself is corrupted, right? Corrupted? No, it is received successfully. Then the station 2 retransmits packet 2 again. The packet is lost. Since the packet is lost here, the ACK packet or NAC packet, whatever is lost, the sender actually does not know the fate of the packet number 2, so it waits for timeout. Until the timeout, the station waits and then transmits the packet 2 again. The receiver acknowledges this one, so we are here. So by this way, the communication or the transmission of packets from sender to receiver keeps going. Now, if we model this one using a discrete time Markov chain, the question is, what will be the time slot? What will be the states of the process, the Markov chain? And once we have the states of the Markov chain, then we have the probability transition matrix. The Markov chain is very simple. Since we have unlimited scope for retransmitting a packet, just a minute. Sorry, here this T naught, actually Ti represents the states, where I represents number of transmissions taken before. That means I indicates already take place, or you can consider this is the number of failures or number of collisions. So when I equal to 0, this indicates this packet did not actually experience any collision or any failures. So this is a fresh packet. When T 1, the subscript value is 1. This indicates this is a retransmitted packet, and previously one attempt was unsuccessful. Now it is the second attempt, fast retransmission. Now, what is the probability that a packet is actually corrupted? A packet is corrupted or experiences an error with probability E. What is E? E depends on two things: the probability of one or more bit error. So if the packet experience, if the frame or packet experiences a single bit error, we assume that the packet is corrupted and the packet actually needs to be transmitted. So E is the probability that at least one bit actually is erroneous. How we calculate this one? Let us assume that the packet size is n. That means there are n bits in a frame, and epsilon actually is the probability of a single bit error. Sometimes we call it BR, bit error rate. And then 1 minus E is there is no error for a bit. So a bit is successfully sent. And this to the power n indicates all the n bits are successfully sent. And when we subtracted it by 1 from 1, then it indicates at least one bit error. So at least one bit experiences an error. And when n is very large, or average number of errors if it is very small, we can consider this one is actually equal to this one. So this approximation is done. Now, the probability that a packet actually experiences a bit error, one or more bit errors, that means packet is corrupted, is E. So when a packet experiences a bit error, the states change from T0 to T1, that means one failure. From T1, we move on to T2, that is second failure, actually first failure here, second failure here, that occurs with probability E. And by this way it goes on. We have actually Markov chain with infinite steps because number of retransmission is not restricted here. And with probability 1 minus E, a frame is or a packet is successfully transmitted. So if the station transmits a packet here T0, and with probability 1 minus E, it remains here, meaning a successful transmission occurs and it goes for the next packet. So by this way, from T1, the failure occurs with probability E, a success occurs with probability 1 minus E. So the chain is very simple, and the chain actually has this one, but once again, this actually is the transpose. You need to consider the opposite one. I did not actually write it here. Now, the long-term probability in a state of pi, the book represented by S, as we already know. Then S has a value, this one. You can solve it very easily to check whether the solution actually is there or not. No, you can try it. It's a very simple one. I think once the Markov chain is here, most of the entries are actually zero. It's a very sparse matrix, and few entries are non-zero. So I think you can actually calculate the long-term probability vector. This actually is this one. This indicates that for T0, the probability is 1 minus E. For T1, the probability is E into 1 minus E. This you will understand that one failure followed by a success. Then T2 will be E square 1 minus E. Two failures followed by a success. And in this way, it goes on. So you'll have a vector. Now, average number of retransmissions for a frame is given by this one. So average number of transmission, if the state is this one, the transmission is 0. If this one, the average number of retransmission is 1. If this one, then the number of retransmission is 2. So first transmission, 1 retransmission, 2 transmission. Number of retransmission is 2, and so on. And this occurs with the probability. What is the probability? This occurs with the probability that the steady state probability of this one, S1, and actually we have a failure. We have an eventual success. So not failure. We have an eventual success. This one. If the success is there, only then we can guarantee that the number of failure is this one. Otherwise, we are not sure whether one retransmission or two retransmission that we discussed in the last class. So 1 minus E is multiplied with S1, S2, S3, and when we are in S1, that means only one retransmission is there. Or when we are in S2, two retransmission, S3. By this way, we can calculate this one, and this becomes the number of retransmission. N of T, N sub T becomes E. And once we have T, then the average number of transmission can be approximated actually by this way. We discussed this one earlier. And this point N is actually E is approximately En instead of that formula 1 minus e to n minus 1. Then the efficiency is actually this one. That average number of retransmissions plus successful transmissions and a successful transmission. So this ratio actually gives you the fraction of time actually success occurs. So it will be one success that requires NT average number of retransmission. That reciprocal of this one actually gives you the efficiency of the system. So when this one is 0, efficiency is 100%. NT is 0, efficiency is 100%. And as we have seen, for this one, N of T is having the value E. So we can actually calculate the efficiency, and also we can calculate the throughput. Similar thing. How it is, the throughput of the transmitter can be expressed as its efficiency. So they define that throughput and efficiency similarly, and efficiency actually we define the efficiency where efficiency is 1 minus En. This epsilon n actually is equal to E, so they actually approximated is 1 minus this one is the efficiency. So this one is the error. 1 minus E is the fraction of time a frame is successfully sent, and the throughput actually is this one. So in ARQ, we actually measure the throughput by actually the probability with which a frame is successfully sent. So this is a very simple mechanism, very simple one. And before we finish the class, let me introduce the next one. Otherwise, in the next class, we will not be able to finish two protocols, go back N and the selective repeat. In case of go back N, as I mentioned, an interesting thing happens. And this interesting thing is that, say you sent 2 packets. You have 3 cases. Packet 1 is successful. Packet 1 and 2 are successful. Packet 1, okay, none of the packet is successful. So none of the packet is successful. This is another one. So when packet 1 is successful, then actually you need to retransmit packet 2. When actually packet 1 and 2 are successfully sent, then actually no retransmission. When none of the packet is successful, then actually you need to retransmit packet 1 and 2. Now, one thing is important. In case of this go back and NRQ, it is not possible that you will actually retransmit packet 1, but you will not retransmit packet 2. The scenario can easily happen here. We consider that packet 1 is successfully sent, so you need to just retransmit packet 2. Both packet 1, 2 are successfully sent, you do not need any retransmission. Here, actually, this star actually is in two cases. You need to retransmit both 1 and 2. If both 1 and 2 are lost, you need to retransmit 1 and 2. If 1 is lost, but 2 is successfully delivered, even then you need to retransmit packet 1 and 2. That's why the name go back and is there. Now, here is the basic operation of the mechanism. What happens? You have a actually window. Following this diagram, we assume that the window size is 3. This means a station can transmit 3 packets without any acknowledgement. If we compare it with a stop and wait actually forces you to transmit a single packet and wait. Here, same thing is there with extension. What is the extension? Now you can actually transmit 3 packets without receiving any acknowledgement. Let's say the station transmit 1, it receives the acknowledgement of 1. Now, actually 2, 3, 4 are also transmitted. Now here we have 2, 3, 4. When packet 2 is sent, a negative acknowledgement is here. So packet 1 is sent, 2 is sent, 3 is sent, 4 is sent somehow. And actually, what happens? Packet 2 is lost and a negative acknowledgement is sent here. So this go back N actually is the mechanism where the receiver acknowledges a number that tells all the packets up to but not including that number is successfully received. The receiver is waiting for that number packet. So the receiver acknowledges this one. This packet has not been received, so the sender retransmits 2 as well as 3 and 4. Now 2, 3 are received. Then once 2 is received, station sends 5. 3 is received, station sends 6. 5. Then 4 is received, station 4. A negative acknowledgement is there. For example, 4 is retransmitted. So this is the basic operation. The diagram is not 100% correct. Just ignore it. Before we finish, we will actually look at the diagram. This is the Markov chain. It is actually a 2D diagram, or you can consider it is a 3D diagram. It's a 3-dimensional actually chain. What happens when you have a window of packet? Let's say you have a window of packets and you are transmitting for the first one. So R0. R1 indicates you are retransmitting the first batch of packets. R2 means you are retransmitting the second batch of packets. What is the batch of packet? We are going here. So these are the fresh packets that you are going to transmit. So how many packets are there? N packets are here. When you transmit N packet, in response to this transmission, the sender will send you acknowledgements, and the acknowledgement will indicate where to go back. The go back N, say this N actually, this N and this N are colliding. So let's say go back N protocol has a number K. If the number is K, that means all the packets up to K minus 1 have been received successfully, and the receiver is waiting for the K packet. So with this example, let's say we have 1, 2, 3. Then when this number, actually, let's say this n has a value 4, and the receiver can acknowledge the number 1, 2, 3, 4, and 5. So when the receiver will acknowledge number 5, this indicates all the packets are transmitted successfully. So this window of packets are successfully sent. It will move on to the second window of packets. Now, if the acknowledgement number is 4, then this indicates all the packets up to 3 have been received successfully. Packet number 4 has to be retransmitted. And this indicates a single packet will be retransmitted. Here is this number. This 1, even though this is 1, actually it is the nth packet. And then when the acknowledgement number is 3, this indicates packet 3 and 4 have to be retransmitted. So we have this packets number here. This one will be the nth packet. This one will be the n-1 packet. So based on the acknowledgement sent by the receiver, will calculate the probabilities. What will happen? The sender will retransmit 1, 2, 3, or all n packets. Here all n packets are retransmitted. Now from here we have, this is second layer, first batch of retransmission. Now from the first batch of retransmission, we move on to the second batch of retransmissions, which is if you have a single packet retransmitted in this here, then either this packet is successfully received, so you from here you go to here and you go for the second batch, or you retransmit the same packet again. If you have two packets retransmitted, you have two cases. Either you retransmit only the last packet, that is you receive the n-1th one successfully, so you will retransmit only one, or you need to retransmit both the two packets, because either this packet has been lost or this and this both are lost. And by this way you will have multiple actually columns here, and then when you have all done, then you can move from here to the next one. By this way you keep repeating, and that depends on how many times you can actually retransmit. That should be a maximum retransmission limit. And here, just before we finish, in 1 minute or 2 minutes, we have a very simple diagram, and we consider that the window size is 2. So you transmit the packet number 1 and you transmit the packet number 2, and the probability P ik indicates probability that k packets are lost among I packets. So if between these two packets 0 packets are lost, that means you do not need to retransmit any of the packets. So with probability P2 0, you go to the second batch of packets, second window of packets. However, with the probability 2 1, you need to retransmit a single packet, and that should be this one. It is not necessary, it is not possible you will retransmit this one. If you have to retransmit this one, then you need to retransmit this one as well, as the name suggests, go back in. So with probability P2 1, with probability P2 2, you need to retransmit these two packets, R12 and R12. So here in the first retransmission, you need to transmit 2 packets. In the first retransmission, you need to retransmit 1 packet. This packet is lost, then 1 of 1, then you need to retransmit. In the second retransmission, you need to retransmit 1 packet, which is this one, will be second packet. On the other hand, here Among these two packets, this packet has been actually successfully sent. So that occurs with this probability 2-1, and you need to retransmit one packets. Or again, you need to retransmit both the two packets. By this way, it goes on. If you have any questions, then you can ask. Otherwise, actually, I need to finish the class here because we have some other job to do. There is a meeting here. Any questions?
No, sir.
I assume no. Thank you very much for your cooperation. And so let's stop the class and see you on Thursday. Hopefully, Thursday I will also take one class, and I will actually upload one assignment for submission of the second part of the term project. Okay. So I will try to communicate with your CR tomorrow, or if your CRs are here, they can call me. Either way, it is possible. So let's stop here. Thank you very much because you have also class with Dr. Ajam. Thank you for joining.